Okay, now we are going to discuss the electrostatic force. Electrostatic force between two charges. And the electrostatic force is given by Coulomb's law, Coulomb's inverse square law. Coulomb's inverse square law. According to this law, the force of the magnitude of the force of attraction or repulsion between two static and point charges between two static and point charges. So between two static and point charges is directly proportional to the product of the magnitudes of the two charges and is inversely proportional to the square of the distance between them. So the Coulomb's law can be stated like this: the magnitude of force of attraction or repulsion between two static and point charges is directly proportional to the product of the magnitudes of the two charges and is inversely proportional to the square of the distance between them. Inversely proportional to the square of the distance between them. Explain this one. Now let us consider two static and point charges. Let us consider two static and point charges. Q1 and Q2 are separated by a distance of small r. Like this. This is Q1 and this is Q2, and the distance between them is small r. Okay, first one Q1 and Q2, and the distance between them is small r. So if these two charges are positive charges, then we can have repulsive force between these two. If these two charges are unlike charges, one is positive and the second one is negative, then we can have attractive force between them. If two charges let them be Q1 and Q2, which are separated by a distance of small r. Now according to Coulomb's law, if F is the capital F is the force between these two, then we can write F is the electrostatic force. Then F is directly proportional to the product of the magnitudes of the two charges. So we can write F proportional to Q1 into Q2. F proportional to Q1 into Q2. And the second point is F is proportional to 1 by r square, square of the distance between the two charges. Force is proportional to the product of the magnitudes of the two charges, that is Q1 and Q2, and it is also inversely proportional to the square of the distance between the two charges. Therefore, we can write F proportional to Q1, Q2 and F proportional to 1 by r square. So, if we combine these two equations in one equation, then we can write F is proportional to Q1 Q2 by r square. Okay. In order to equate these two, we have to consider a constant. Let that constant is denoted by 1 by 4 pi epsilon naught into Q1 Q2 by r square. So this is the expression for the force, electrostatic force between the two charges Q1 and Q2. So here 1 by 4 pi epsilon naught is the constant of proportionality, and this epsilon naught is called as the permittivity of free space. This epsilon naught is called as permittivity of free space or air. Permittivity of free space or air. Epsilon naught. So this is the expression for the electrostatic force. F equal to 1 by 4 pi epsilon naught into Q1 Q2 by r square. Here F is only the magnitude of the force between the two charges. That is the only magnitude of the force between the two charges. Okay. If we want to find the direction of that force, we have to take into consideration the types of charges. The type of charges on the two bodies. Okay, so this is the expression for Coulomb's inverse square law. Okay, next one, if the two charges are separated by a medium other than free space, then the force between them can be written as, then F is equal to 1 by 4 pi epsilon into Q1 Q2 by r square. Okay, you can see the difference here, epsilon naught, and here we are considering only epsilon, because epsilon naught denotes the permittivity of the free space, that is when the two charges are separated by air, we consider epsilon naught. If the two charges are separated by medium, that is other than air or free space, then the expression will become 1 by 4 pi epsilon into q1 q2 by r square. Here epsilon is called permittivity of that medium. Epsilon is called permittivity of that medium. Okay. So this is about Coulomb's law, Coulomb's inverse square law. It deals about the force between two charges. Okay. Here epsilon naught is the permittivity of free space, and its value is given by 8.85 into 10 power minus 12. 8.85 into 10 power minus 12, and therefore we can have the value of 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. If we substitute 8.85 and 10 power minus 12 in this formula, we can get the value of 1 by 4 pi epsilon naught is 9 into 10 power 9. 9 into 10 power 9. Here 1 by 4 pi epsilon naught is the proportionality constant. These two values, we have to remember these two values. Epsilon naught value is 8.85 in 10 power minus 12, and 1 by 4 pi epsilon naught value is 9 into 10 power 9. Okay. And in vector form, the Coulombs force F can also be called as Coulombs force, electrostatic force or Coulombs force. So in vector form it can be written as F bar is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square into R cap. Q1 Q2 by R square into R cap, or this can also be written as F bar is equals to 1 by 4 pi epsilon naught into Q1 Q2 by R cube into R bar. So these two formulas are in the vector form. 1 by 4 pi epsilon naught into Q1 Q2 by R square into R cap, and 1 by 4 pi epsilon naught into Q1 Q2 by R cube into R bar. Okay, this is Coulomb's inverse square law. It deals about the magnitude of force between two static and point charges. Okay, here to find out the force between two charges, the charges must be static. The charges must be static and point. The charges must be static and point. These are the two conditions to apply or to find out the force between two charges by using Coulomb's law. Or else we can also say like that, the Coulomb's law can be applied to static and point charges only. These two are called limitations of Coulomb's law. Limitations of Coulomb's law. charges must be static and point charges. These two are called limitations of Coulomb's law. Okay, let us see now what happens if we don't take static or point charges. If the charges are not static and point, what will happen? Okay, first one, if the two charges are not static. Not static means they are moving. They are in motion. Okay, they are in motion. We have already seen that a charge in motion, whether it is uniform or non-uniform, it produces not only the electric field but also magnetic field. Okay. When the charge is at rest, it produces only one field, that is the electric field. But when it is in motion, it produces magnetic field along with the electric field. And that magnetic field changes the electrostatic force between the two charges. Okay. So whenever the charge is in motion or the charges are in motion, that moving charges produces magnetic field along with the electric field, and that electric field will change the electrostatic force between the two charges. For example, if Q1 and Q2 we are considering the two charges, if Q1 is moving in this direction with a velocity of V1 and Q2 is also moving with a velocity of V2 in this direction, then what we can have is, when it is moving in this direction, the electric field will be in this direction E1, and the electric field due to the second charge E2 will be also in this direction. But with the electric field we can have magnetic field B1, here also magnetic field B2 in the perpendicular direction. Okay, so these two magnetic fields will affect the electric field, the force, the electrostatic force between the two charges. Okay. Similarly, if the two charges are not point charges, that means they are distributed. Like this. The charges are distributed like this. Then if we find the force between these two charged bodies, and this is the point charge Q1 and this is point charge Q2, this is the distributed, this is Fp, and this force is different from this force. This is the force between two point charges and this is the force between two distributed charges. If we find the force between these two cases, in the case of distributed, force will be different from the point charges case.